in 102, I got pretty much to the end of class and realized I had not been recording because I didn't have this reminder service. And I ended up having to redo it the next day. And giving a business calculus lecture is mind-numbing even once. Okay, get my notes going too. Of course, probably you all are thinking, oh yeah, try business calculus mind-numbing, try college algebra. Okay, let's make this a little bigger. Yeah. And there's something else I wanted to bring up. I've mentioned, with the event that's coming up on Friday, my friend Dr. Gerritsen speaking at 1 o'clock, and hopefully you all, or at least a good subset of you all, can attend. I do want to mention that given the general tendency of USM students to be very much the quiet bunch, that I hope that is not what happens on Friday. So, because it is meant to be not just a professor showing up and giving a talk like they would about the research, but really a discussion between professor and students, and therefore it should be a two-sided affair. So just something to keep in mind. Okay, now, so what I showed last for numerical differentiation is coming up with an approximation of this form using Taylor polynomials with the remainder to get the error. And so what I'm going to do today is show how to get numerical differentiation formulas that have this same form, but they that have the same form, but they're derived in a very different way using something that you are already familiar with, and that is Lagrange polynomials. Okay, and they produce the same kind of formulas, but you might find these advantageous, and certainly this illustration will be used as Lagrange polynomials for building approximation formulas for derivatives, as we'll see today, and also integrals. Okay. So I'm checking how I title my sections here. Okay. So these numerical differentiation formulas, such as a forward difference or backward difference, or this other one, this one-sided formula that I derived last time. I need to mention the term we use to describe all of them. They're called finite difference formulas. Okay, because the resemblance to the definition of derivative that uses an infinitesimally small difference, because the definition of derivative involves taking the limit as h goes to 0. What we're doing here is we're not letting h go all the way to 0. We have some finite number h, a finite spacing h, instead of something infinitely small, and using that kind of difference quotient to obtain an approximate derivative. So they can be derived using, as I mentioned earlier, Taylor polynomials, or Lagrange polynomials. So what the idea is, so we have an approximation that's of the same form as before. So f prime x naught is equal to sum we have a linear combination of values of f at select points. Okay. So here's what we do. I forgot well, let's see. Actually, I'll leave it like this. Now, sometimes I put a 1 over h out here, but that's when I'm assuming equal spacing. In that case, it's just notational convenience. But here, I'm not making an assumption. These x values can be anything. Okay. So what we do is, so however many points we use to the left and right of x naught, as I remember from last time, points of negative indices are to the left of x naught, points of positive indices are to the right of x naught. So if I let n equal to j plus k, so then I have n plus 1 points all together. So then what I will do is I will let Pn of x be the nth degree polynomial, interpolates f of x at all of these points. Okay. Okay. And it makes sense because I have n plus 1 points. Therefore, if I fit them off a polynomial, that would give me degree n. So then I have the following, that f of x is equal to Pn of x plus error. What I'm going to do is I'm going to represent Pn of x in Lagrange form. So now I can say f of x is equal to sum of f of xi, so right so far it's matching this, times the Lagrange polynomial of degree n, number I, at x. And then what I have here is the interpolation error. And that's the error formula that you've been dealing with lately in the homework. So that would be f n plus 1 of some unknown point, c of x. And I call it c of x, or squiggly of x if you like, because it depends, the unknown point depends on x, over n plus 1 factorial. And then we have this product of linear factors, x minus xi. All right, so this is Theorem 741, that error formula right here. Okay. So I have this representation of f of x, but I want f prime at x naught. So to get everything we want here, and what do I mean by that? By everything, we want the approximation of f prime at x naught, and we want an error formula. all we got to do is take a derivative of this, and then substitute in x naught. So we have f prime at x naught. All right, so if I take the derivative of this sum here, well, f of xi, now keep in mind, f itself may be a function of x, but what have I done here? I've plugged in xi already. Therefore, for purposes of differentiating with respect to x, this is a constant. So I have just plain old f of xi here. That doesn't change. I do take the derivative of a Lagrange polynomial and evaluate that at x naught. So if we compare this to what's up here, these are the coefficients. The coefficients are a finite difference formula that'll have an h in the denominator. H in the denominator if equally spaced. They come just from taking a derivatives of a Lagrange polynomial and evaluating at x naught. So whatever problem you're trying to solve, taking a derivative at x naught in this case, we just solve that problem for the Lagrange polynomials, and those are our coefficients. Then what needs to be done is, and I'm going to introduce some strange notation. You may have seen this elsewhere, but I want to make sure you're aware of it. I need to take the derivative of my error formula here. Okay. But what I also need to do, just like I did over here, I took the derivative and plugged in x naught. I need to do the same thing over here, but just kind of not need to express in proper notation. But here's proper notation for you. That this vertical bar signifies evaluation. Now you may have seen this elsewhere. Certainly comes up in calculus where vertical bar is used to indicate plugging in limits to for a definite integral, but it's used in other situations too. So what all this means is take a derivative of this whole expression with respect to x, then after that substitute in x equal x naught, and doing that over here gives you the approximation. Doing that over here gives you the error. Now, I'm actually not going to carry out the full evaluation of this error formula here because that's a homework problem that I've actually assigned. So you get to have the pleasure of doing that. One thing I want to point out is, as you do it, it may seem like a bit of a mess, but don't get discouraged. It will simplify a fair amount once you do this part of plugging in x equal x naught. So keep that in mind. Okay. So that's it. That's it. We have what we need. We have our approximation, and we have our error formula. So what I'm going to do now is an example. Oops. So what I'll do is I will let j equals 0, so there are no points to the left of x naught, and then x1 is equal to x naught plus h, and then x2 is equal to x naught plus 2h. So here I will assume equal spacing. So k is equal to 2 in this case. So So it's actually the same situation as this. I'm going to arrive at the same formula, just in a different way. Okay. So here's what we have. Just applying this right here as much as we can. All right, so I have fx naught, Lagrange polynomial of degree 2, the first one, so index 0 at x naught plus f of x naught plus h. Second Lagrange polynomial plus f of x naught plus 2h. Third Lagrange polynomial prime at x naught plus the error, which will not fit on this line. Actually, I need to move this whole thing to a new page. So the error all right, so that would be whoops. Okay. All right. So what we have here, it's this error formula where n is equal to 2. So the interpolation error would be f triple prime at an unknown point over 6, 3 factorial. So x minus x naught, x minus x naught minus h. Okay. So this would be interpolation error in that case, and so we have to take the derivative of this in respect to x and evaluate it at x naught, and that would be the error. So I want to point out that if we look at the error we got last time, we did have a third derivative. So we see where we're going to get that again. But here we had 2 terms, and I wanted to combine them into one, but because of a minus, I could not use the intermediate value theorem to justify that. But if you were to work out this derivative here, and this is, like I said, you'll do this in a more general sense in the homework, what you'll actually end up with is just one error term that has f triple prime. So that's going to be a lot nicer. Now, we saw the error above also had a factor of h squared. We don't see that here, but once you do take the derivative of this and plug in x naught, you'll see that you will get some factors of h. So it will turn out to be second order accurate like before. Okay. But what I want to show you now is the process of getting these coefficients. All right. So if I write out what the first Lagrange polynomial is, give us an idea of what we're in for. Okay. Now, remember how Lagrange polynomials work. That there's a fraction, and then we had to construct in such a way that this is equal to 0 at, in this case, 2 of the points, and it's equal to 1 at the other point. So this one, Lagrange polynomial, should be equal to 1 at x naught. this should be equal to 1 at x naught plus h. This should be equal to 1 at x naught plus 2h. So who can tell me what I should have here? It's like starting with the numerator in Lagrange polynomial to make sure that it's equal to 0 where it's supposed to be. Remember, we write the Lagrange polynomials in factored form so that we can just stipulate here's what the zeros are. Made a shot.
Mute what you said again.
Okay.
Thanks.
All right. Okay. So this look. What do we have for the numerator here? Because we write this in factored form, so that we can just say here's what the zeros are supposed to be. And remember, these are our points: x naught plus h, x naught plus 2h. And each Lagrange polynomial will be equal to 0 at 2 of these points, and 1 at the other one.
So wouldn't that be 0 x naught? The first term?
Okay. I think some words got dropped there.
The first term disappears, right?
Wait. First term? Are you looking here? You mean?
Or I remember when we were doing the Lagrange polynomial, you like do the other two.
Yes. So
point.
here,
Yeah.
this is now here's our points: x naught plus h, x naught plus 2h. That's the ordering. Here we're doing the first Lagrange polynomial. So this should be equal to 1 at the first point, equal to 0 at the second and third points. But yeah, what you just said, like we make it 0 at the other points.
Mm-hmm.
So what linear factors do we put in here in the numerator?
X minus x naught minus h.
Yes.
And then x minus x naught minus 2h.
Yes. Great. Okay. And what about down below to make sure it's equal to 1 where it's supposed to be 1?
I guess the same thing, right? If we want it to equal 1.
Yeah, almost exactly the same. What's the one tiny difference?
Are we plugging in x naught on the
Yes.
bottom? Yeah, for the x.
Yes. Okay, and of course we see in this case there's some obvious simplification. I'll just fill that in. Dang it. Okay. So down below, this will simplify to the x naughts cancel, so we have minus h and minus 2h, so ultimately 2h squared. Okay. So then what you would need to do from this point is we need a derivative of this at x naught. So So we look at this. All right, so first focusing on just taking a derivative of this. And right now I don't feel like multiplying it out. I'm just going to use the product rule. All right, so we have 2h squared down below. So we're going to have this. So x minus x naught minus 2h times the derivative of this, but that's just 1. Okay, and then plus this times the derivative. Yeah, for purple book there. Yeah. Yep. All right. Minus h. And that's it. That's the derivative. So that worked out pretty nicely. And then we'll go ahead and substitute in x equal x naught, which is going to cause some cancellation. So what we're going to get is minus 2h here, minus h here. So minus 3h over 2h squared, then we can just simplify. Okay. So here we go, minus 3 over 2h is a coefficient. And now, let's compare, because this same differentiation rule was obtained before. Here we have for coefficient of f of x naught, minus 3 over 2h. So that worked out as it should. So questions about what happened there? Now what I could do is just go ahead and do the same thing for the others. But just for fun, I'm going to show you a slightly different approach. Now the interpolation points are equally spaced. X naught plus h, x naught plus 2h. We can use a change of variable for convenience. So I'll define a variable s equal to x minus x naught divided by h. So if I use this change of variable on these values here, so this change of variable maps x naught plus h, x naught plus 2h to what? Okay, so if x is equal to that, what are the corresponding s values that I would get?
The first one.
Oh, sorry, the audio.
The first one should be 0, right? Because, yep. And then I have to work my stuff on paper.
Okay, fine. If you want to do that.
Plus h minus. So the next one's 1, and then yeah, and then I guess just 2. Yeah.
Yeah. So now we've mapped our points to the integers. So we work with those Lagrange polynomials. So if I define these modified Lagrange polynomials, well, I'll call it, just to distinguish, I'll call it tilde L, which is a function of S, would be equal to the corresponding Lagrange polynomial that's a function of X. We have a following that what we really want, of course, is the derivative of the original Lagrange polynomials at x naught. But that would be equal to the derivatives of these modified Lagrange polynomials at 0. Since x equals x naught corresponds to s, oh, sorry, I need a derivative here, at 0. Now, before I go any further, there's actually something wrong with this line. I'm missing something over here. Can anyone tell me what it is? I'm going to write these a little differently.
Do we know our I?
Sorry, what?
Never mind.
Okay. That's okay. You gave it a shot. Anyone else want to give it a shot before I drop a hint? All right. Now, I could write this derivative here as derivative with respect to x. I could write this derivative respect to s. Well, I should fix my notation here. Evaluated at x equal x naught over here. And this one evaluated at s equals 0 over here. So what do I need to include in this formula to make it correct? And actually, no one should feel bad about not seeing it, because this is actually the exact same issue back when I was an undergrad researcher working for the chair of a computer science department and a numerical analysis legend, John Rice, that he had a formula pretty much like this, where he had left out the thing that I'm asking you about, and the mistake went unnoticed by a very long time until I, the lowly undergrad, pointed it out to him. Anyone?
I don't know if this is silly, but h can't be 0.
That's not the issue.
No? Okay.
It has to do with the fact that I've made this change of variable from x to s. And what does that mean for derivatives?
We have to multiply by the derivative of s.
Yes, excellent. All right, gold star for you. Yeah, but here I take a derivative with respect to x. Well, derivative of this with respect to x is dds times ds d. Wait. Okay. Yeah. Sorry. D. Yeah, derivative of s with respect to x. Since we have a derivative of x over here, so the derivative, what we're differentiating has to match up. Now, can you tell me what would this be?
And the ds cancel, right?
Oh no, we're going to focus only on ds dx.
Okay.
So then you have to refer to the change of variable formula and get the derivative from there.
Is it just 1 over h?
Yeah. Oh, aren't you on a roll? Okay. Really, working with these Lagrange polynomials that are just interpolating into integers gives us the numerical part of a coefficient, and then the 1 over h factor is thrown in by virtue of a change of variable. So now, let's take a look at the I equals 1 case. Now we're talking about the second point. So we're interpolating at 0, 1, and 2 in that. Those are our interpolation points in that order. So degree 2 polynomial number 1, so that's the second in the list of S. So if we're interpolating at these points in this order, and we want this to be equal to 1 at the second point and 0 at the other two. So this will be a function of S now. What would we get? Oops, that's supposed to be a fancy L. So doing the Lagrange polynomial the same way as up here, except using 0, 1, 2 instead of x naught plus h, and x naught plus 2h.
So x minus 1 and x minus 2 on top.
We're focusing on the second point here. And remember, it's a function of s, not x. So we want it to be equal to 1 at the second point.
S, the first one.
Yeah,
Just-
or S minus 0, yeah.
Right. And then, oh, sorry, I was ignoring the 0 since it's minus, but okay. And then S minus 2.
Yeah.
And then replace then 1 minus 0, 1 minus 2.
Yep. Okay. So now we can clean that up. Yeah. So yeah, it could be S minus 1, S minus 2 for the first polynomial, but we're doing the second one. So we have S times S minus 2, so that's going to be S squared minus 2S all over, okay, 1 times minus 1. Okay, so let's clean that up. So that'd be 2S minus S squared. All right, so that's our Lagrange polynomial. So the coefficient, which is now given by this, so the coefficient of f of x naught plus h in our finite difference formula is 1 over h times the derivative of this modified Lagrange polynomial evaluated at 0. So what we get is take the derivative of this, so that's going to be just 2 minus 2s. Evaluated at s equals 0. Oh, and I can't forget the 1 over h. So we just get 2 over h. Okay. So then if we compare from when this is derived previously, yeah, that's the coefficient. Something is off here. Okay, all right. Yeah, this coefficient turned out to be 2 and then over h. So here we have 4 over 2h, but that's the same as 2 over h. So all of that works out. Okay. So then the coefficient of f of x naught plus 2h we need the third Lagrange polynomial, which is
S minus 2. S minus
sorry, it dropped out.
minus 1.
Yes. Okay.
2 minus 0, 2 minus 1.
Okay. All right, so we get s times s minus 1, so that's s squared minus s all over 2. All right, so then we take the derivative and we get 2s minus 1, but then we have to plug in s equals 0. So that would be minus 1/2. Well, we have to divide by h, so minus 1 over 2h. And so if we look at all the coefficients we have minus 3 over 2h, minus 1 over 2h, and then plus 2 over h. And all of those coefficients sum to 0, So so overall, we have f prime x naught is equal to, so we have a common denominator of 2h. So we have minus 3 f of x naught plus 4 f of x naught plus h, because 4 over 2h, that's 2 over h, minus f of x naught plus 2h, plus the error. And it's not something I've derived because that's something I've deferred to the homework. What the error turns out to be is f triple prime at an unknown point all over 3 times h squared. So this is second order accurate. So once you, now the error formula, it is so the error formula is from equation number 9.6 in the book. But one of the homework problems is to take that error formula and specialize it to the case of equally spaced points. And that's how this would come out. So questions about what happened here?
So when you start the problem, you said you switched a method, like methods just for fun, but we could do it, we could have continued going about it with like x naughts and what so forth, x naught, x1, x2.
Yeah, so I don't really care if you
Or
this way or the other way. Actually, I don't know if I gave a homework problem specifically deriving a rule like that, but if I did, then yeah, I wouldn't care. But I wanted to make y'all aware of this general approach of making these kind of changes of variable, because they could be useful in a number of situations just to reduce clutter.
that being said, you said earlier we can only do this change of variable because of equal spacing. So if this wasn't equal spacing, we couldn't do this?
Technically you can, but then how would you define the change of variable in that case? That's the thing.
Right. It
Yeah.
seems like it would be an issue, so like it would only be practical with equal spacing.
Yeah, just because you want a simple change of variable formula. Because look at what the derivative we got. It's just plain old the ds dx is just 1 over h. So if unequal spacing, you either have to have a more complicated change of variable formula, or you end up not interpolating at the integers. You might be interpolating at other real numbers, and then what do you gain? Because and really, but then again, the only reason you'd use a change of variable, even in this case, is if you're working this out on paper, and you well, actually, that's not necessarily true. It's not only useful for working things out on paper when you want to work with nice numbers and less cluttered formulas, but it can also help in code. That you might have if you're writing a program that grinds this out. And actually, that is one of the problems that I've given, is writing a MATLAB function that computes these coefficients. Although I think, oh, you know what though? The problem I assigned has you do it using Taylor series, not Lagrange. And there's another problem in the section that I did not assign that has to do it using Lagrange. So for something like that, the code would be a little simpler if you write your code in such a way that uses this change of variable. So basically, I'm just I'm inserting another arrow in your quivers of something that might be useful.
Okay.
Alrighty. And my plan is for you to have quivers so full that you won't be able to walk by the time I'm done with you all. Okay, Ever questions about all this? Okay. Now, so far, I've only talked about coming up with approximations for the first derivative, but we can use the same approach, either Taylor series or Lagrange, for second derivative. The tips. Okay. So suppose we use these points, f of x naught minus h, f of x naught, f of x naught plus h, to approximate f double prime at x naught. So, and I can use either approach that I've shown you, using Taylor expansion. I'm always reluctant to say Taylor series in this context because Taylor series suggests letting the Taylor terms go off to infinity. But we always want to truncate. We always want to use a remainder because that's important for error. So this isn't really Taylor series per se, because we don't go to infinity. So if I write out Taylor expansions of these 3 points, okay, so we have f x naught minus h, then f of x naught will just be, whoops, f of x naught will just be f of x naught, nothing to do there, and then f of x naught plus h. Okay, so f of x naught minus h will be f of x naught minus h f prime of x naught. Okay. Plus 1/2 f double prime x naught h squared minus 1/6 f triple prime h cubed, and then plus 1/24 f fourth derivative at an unknown point, which I'll call C1, times h to the fourth. So that's a remainder, so that's where I'll stop. And then I have the same expansion for f of x naught plus h, where it's got to change the signs. And I have a different unknown point over here. Okay. So what I can do is, if I take the first and last lines and add them, then the f prime terms cancel, the f triple prime terms cancel, but nothing else will cancel. The second derivative terms will add. So I'll have f double prime times h squared. The f terms will add. But then what I can do is I can subtract off 2 times this and get rid of it. So in other words, what I will have here is f triple prime, double prime at x naught will be equal to f of x naught minus h minus 2 f of x naught plus f of x naught plus h all over h squared. So for first derivative, you got to divide by h. Second derivative, you got to divide by h squared. So if I take this linear combination of all these Taylor expansions, look at the coefficients, 1, 1, and minus 2. they sum to 0. Therefore, the f of x naught terms will go away. You can already see by adding these two, these terms go away. Here I have just f double prime of x naught h squared. So I divide by h squared to get these to add to what I want. These cancel. What's left here, it will give me my error. Here I have h to the fourth, but I have to divide everything by h squared. So my error will be of order h squared. So what I will get is (1/12) fourth derivative at an unknown point times h squared. Now to explain everything that comes from here, the minus comes because I'm going to get f double prime of x naught on this side. These terms get moved to the other side. That's the minus. 1/24 plus 1/24 is 1/12. So just adding those and dividing by h squared gives me the 1/12 and the h squared. And then what I have, okay. And the reason why I'm able to combine these into one is using the intermediate value theorem, as I did in a previous example, to replace. If I could think of these as basically expressing in terms of the average of these two values, and if f fourth derivative is continuous, there's some point in between xc1 and xc2 where fourth derivative is equal to that average. So it all plays out the same way as what I did here on Monday. Because notice that allowed me to combine these terms to get one error term. Okay. All right. Now, so questions about what happened here. All right. Okay. So this is using a Taylor approach. You can also use Lagrange approach. What you do is you compute the second derivative of each Lagrange polynomial and evaluate at x naught to get the coefficients in your finite difference formula. Now, one drawback of Lagrange approach is that unlike first derivatives, in first derivative it's not too difficult to get a concise error formula. But with using Lagrange of higher order derivatives, it's a bit more difficult. So an alternative is given in a homework. Alternative way to obtain an error formula such as this. And actually, it's something that will be familiar to you. You're actually going to be using an approach very similar to what you've just done in dealing with Urban interpolation, using those freaky phi functions, like 5t. So having gone through something like that, and using Rolle's theorem, etc., that hopefully that prepares you well for this problem here that I've given. So it is a strange approach, but because of what you've done in the homework, hopefully it'll seem less strange. Okay. Okay. Making sure that there isn't something else that I'm supposed to be including here. Okay. Well, it's past 5 o'clock, so everybody's probably pretty drained by now. One thing I want to point out, though, about these error formulas, about sensitivity, numerical differentiation is, and we'll really be able to go into detail on this, is an ill-conditioned problem, meaning that results of approximating a derivative using formulas like these are very sensitive to error. Like if there's an error in a function evaluation, that could lead to a larger error in the derivative. Also, the error formulas in these finite difference approximations, like the one we see here, they do not take round-off error or really error in evaluation of f into account. So these finite difference formulas and their accompanying error formulas do not they assume that these values of f at x0 minus h, x0, etc. are exact. But in an actual computing environment, these will not be exact. And any error that occurs in these expressions can get amplified considerably. So 9.1.11, the last homework problem from this section is it's a relatively simple problem because all it asks you to do is try some things in MATLAB. Basically, you're trying things into prompt. You don't even have to write like a M file, and giving your observations as to what happens compared to what you expect or hope will happen. Things go awry, and so this sort of thing can happen that because you might think, okay, as h is getting smaller, that your results should be getting more accurate. So this homework problem will get you closer to the full story about that. And the thing is, a lot of numerical analysis, even though there's coding involved, is worked out on paper. A lot of theory involved, and sometimes that theory doesn't translate well into practice because you have to account for everything, all the different sources of error, and the theory that we have, such as what I've shown you, doesn't necessarily do that. And accounting for round-off error can change a picture pretty drastically, at least in some cases. And this is why, like for example, when you learn to, and I think I might have mentioned this early in the semester, but when you learn to solve systems of equations, like in linear algebra class, you learn about Gaussian elimination, and so and that's what people have been using for centuries, and doing it on paper. And then when computers were invented, like, okay, let's implement Gaussian elimination on a computer, and then things would go badly sometimes, and they would see, oh, because of accumulation of round-off error, and they were afraid that Gaussian elimination would not be viable because of error in arithmetic that they didn't have to account for before when things were done on paper. So it was eventually proven that it is stable, that round-off error can be contained, but it is still a significant issue. Okay, so this concludes numerical differentiation, and what will happen for the rest of the semester is numerical integration, where we will again deal with Lagrange polynomials that will be very helpful for this, because there are different problems where you're trying to solve a problem such as a derivative or integral for a generic function f of x. So what do? You would just want an approximation. So you approximate f by a polynomial, and then you solve a problem exactly for a polynomial because it's easy to do in these cases. So what we really have is that the derivative or integral. So what happens is the approximation of a derivative or integral is the exact integral or derivative of the approximation, in this case, a polynomial approximation. So a lot of techniques are based on that idea. That's because polynomials are so much easier to work with, but also some complications can arise. So that's what I'll get into starting next week, is basics of numerical integration and seeing some more sophisticated ideas from there. Okay. So like I said earlier, next week, I feel like what I have to cover during that week is going to be a bit more straightforward than this. So I'm hoping that if I don't ramble too much, sorry if I do, we'll have some time during class for homework. But of course, you all know to bug me outside of class too, and all of you are good about doing that. So we'll just we'll just get through the rest of this. All right. So last chance for questions about anything. Or about homework or whatever. Okay, I think it's enough awkward silence. So, all right. So, well, good luck with all the stuff I've dumped on you, and then I'll see you all on Monday.
Thanks.